BSides DC would like to thank all of our sponsors, and a special thank you to all of our speakers, volunteers, and organizers for making 2018 a success.
My name is John Dunlap. This is a talk called The Exploit Factory. It's kind of about how you can DIY yourself a little compute cluster to do some fuzzing, to find some vulnerabilities, so you might make some exploits. This is more for if you have a hobby of fuzzing, or maybe you're running a small business and you're looking to spend a few $100s a month on having a very powerful fuzzing rig. And as a secondary concern, thinking about what kinds of optimizations that we could learn from the scientific computing world and apply to the fuzzing rig that we're going to build in order to get some kind of gain, right? Instead of just having the off-the-shelf images or whatnot, try and do something to our fuzzing setup to make it run faster. Maybe at the cost of a little extra engineering time. You know, say we're a at-home security researcher like myself, and we want to use some of our acumen to get more return on our dollar. That's what we're going to talk about here today. This is me, I'm John Dunlap. I hack like this. I find CVEs. I like to do binary exploits. I like to do fuzzing. I like to do reverse engineering. And I also do a lot of biohacking. I did a talk at Defcon earlier this year about encrypting data in living organisms, like editing E. coli bacteria and putting ciphers in them, which is pretty cool stuff. Here's my formal About Me card if you're interested, with all of my personal details if you want to get to know me. If you want to check out my previous talks, here's some links to that. It's all on my GitHub if you want to check them out. But, you know, DNA encryption, machine learning, FPGAs, and the history of hacking, even deep dives into that, 3D printing security, and jump-oriented programming gadgets for exploit development. So I do a lot of research, researcher, pen tester, reverse engineer. And by the way, while we're on the topic of talks, did anyone go to Defcon this year? Anyone else covered in sand for a couple days? It was great. I think I can still taste that sand. It took a while to get it out of my teeth. So who is this talk intended for? As people who like to do fuzzing and do it faster, I think over the last couple of years, everyone's discovered that AFL is this magic beast that finds bugs, but sometimes it's slow. Some platforms, it's extra slow. For some kinds of software, it's completely non-viable. This is for people interested in wanting to get more out of their fuzzing sessions for the money they're putting into it. I'm one of those guys who has to take everything way too far, and as soon as I started doing fuzzing stuff, I thought, how can I make a Beowulf cluster? How can I put way too much compute power at this? How can I over-engineer the daylights out of it? And that's kind of what I did. It's interesting to experiment with and explore where you can get a little more bang for your buck. Now, here are my motivations for this talk. I was limited in my fuzzing setup. I wanted a semi-automated system. I wanted to be able to throw jobs like a job queue at AFL, because if you've ever used fuzzers, there's a setup process that's kind of time intensive. You have to find a way to throw stuff at it. And I wanted something that could be replicated, basically, without a lot of overhead. I ran into a lot of problems doing 3D printing research. There's this whole ecosystem in the 3D printer world of slicers, which, if you've never used a 3D printer, what a slicer is kind of like a compiler that turns a 3D model into a set of instructions that the machine can understand. It's kind of like the same stuff that CNC machines use. It's called G-code. And I found that there was a lot of vulnerabilities in the software, but the software ran so slow that it was a little immune to fuzzing, and it wasn't so helpful at automation stage. So in this talk, we're going to explore techniques for porting high-performance scientific computing optimizations for small business or individual fuzzing rig. We're going to evaluate each of the standard techniques that people would learn in like scientific computing, accelerated class, and see if they offer any benefit for our purposes whatsoever. And see if we can get more crashes per hour of compute time, and see if we can't get better crashes, and see if we can't have some better optimization which limits the pain of setting this up. Now we're going to define some trade-offs. Everything in engineering is a trade-off, right? We can't have everything. And the way that a lot of people or companies would approach this situation is just throw power at it, right? Why prematurely optimize when you can just throw a couple more CPU nodes at it? And for me, I'm not made out of money. I'm willing to spend an inordinate amount of money on this for some reason, but because I'm fascinated with cluster computing and optimizations and optimizing compilers and stuff. But what we're going to try and do is not spend all the money. And what we're going to try and do is take the money we have and trade engineering time to get a profit. All right. Here's some previous fuzzers, actually, just for time's sake and complexity's sake. I'm not going to get too deep into these. Hopefully there'll be a version of this talk someday where I benchmark my system against others, but I didn't. And honestly, they're not quite optimized in the same way that I'm looking to do. These kind of micro optimizations are honestly in a more widely applicable system, not super advisable, because you're going to trade a lot of engineering time for what you get. But I like to tinker, so this is fun, and I think a lot of people will get something out of it. So before we get too deep into the application side of this, let's talk about, in general, some high-performance computing optimization techniques. Sort of like if you were going to take a class on scientific computing, what kind of techniques would you learn to optimize your C code to make it faster? We're not generally talking about like big O optimizations for algorithms. What we're talking about is things like optimizing for cache, that kind of stuff. We're going to go over this in detail, and then we're going to go over how we can apply those optimizations to a fuzzing scenario and whether it helps at all and what scenarios it does help. And just keep in mind, this comes from an optimization script kiddie. I never worked for Sandia or anyone like that. I just took a couple of the Intel classes, bought the Intel optimizing compiler, and learned everything I could about how to apply this stuff. You know, so please enjoy my lead techniques, if you will. Also, just as a warning, you might hear a lot about these guys. I'm not trying to advertise for them. It's just kind of what's out there. If you're looking to write super fast stuff, it's just going to come. So let's do a quick overview of the categories we're going to talk about in terms of optimizations we're going to do on our system. So we might look into applying SIMD optimizations, which is same instruction, multiple data, sort of parallelization of a sort. We might be doing threading, OpenMP. We might be doing optimizations for cache, various kinds of multiprocessing, GPU acceleration, perhaps explore some FPGA acceleration, and optimizing compilers. But what we're not generally talking about are improvements to the algorithms themselves. And the reason that is that, number one, finding a fuzzer that generates better test cases isn't the point of this talk. What we're trying to say, given the test cases we have, how can we generate them faster, or how can we get through the program execution state faster? So that doesn't necessarily give us control over the algorithm we're using and improving on that level. I think everyone's right to point out that improving the algorithmic complexity is the best way to do this before micro-optimizing things. So let us move on to the individual optimizations. So I think a lot of people who do C programming have heard of SIMD optimization, so I beg your pardon, I'm going to describe it a little more detail that is probably necessary for people who are not familiar with doing this kind of thing. But we're talking about same instruction, multiple data, or Intel, AMD style assembly instructions that allow us to do essentially addition, multiplication on vectors instead of scalars. your compiler already does optimization like this, but it's imperfect. Compilers have to be conservative in their behavior. They can't optimize when it's potentially unsafe. They can only optimize when it's provably safe. And that means they leave out a lot of opportunities for what we can do. And if we want to trade our engineering time for computer time, like if we think we can make a good engineering decision to optimize further, we might save a good bit of money where it applies. If this helps you sort of visualize what SIMD is in terms of registers. You might have, we're used to like 16, 32-bit registers. We might have up to 5 12-bit registers. And when we're doing things like matrix multiplication, like a very thorough SIMD optimization might really give us some degree of speed up on the order of like 10 or 20%. And of course, like C programmer people in the audience are like, you can't do that, the compiler will always do it better, and it's just not true. I'm not going to entertain that. Like I just said before, it only sometimes does it do it. It has to do it conservatively, and we will find situations where we can help ourselves by doing it manually. And hopefully the compiler we're using or the library we're using sort of enables us to do that efficiently. So if you're wondering about like the general case, because when I got into this, I'm like, how do I find the cases where this doesn't happen easily? Conveniently, if you use the Intel optimizing compiler, it will just tell you. It will look at every loop in the entire program and say, I gave up. I didn't do it. But if you're manually looking through code and looking for situations where the compiler is giving up, you're looking for data dependency situations, right? So in many cases, the compiler decides that one piece of data is unsafely dependent on another. I'll show that in a second, but if the compiler thinks that, it will never try to optimize it. But in a lot of situations, we can teach the compiler that it's okay, or we can just manually do things. So here's a case for y'all to get you thinking about it, of what a unsafe parallel situation would be. This is like Fibonacci sequence. Most people are familiar with this. It comes up on like coding interviews and that kind of thing. And in this case, because we're computing things based on previous values, we can't do it all at the same time. Right? It's linear. That in this case, we can't refactor things into matrix multiplication. So keep that sort of dependency in mind when we're thinking about how can we speed up fuzzing on our compute cluster, right? Is our operation linear, or can it be put together as sort of refactored into the format of matrix multiplication? Threading, we're going to use some context switching, switch with other pieces of process, but it's non-deterministic. We can't count on any particular timing of the threads. We can use a library like OpenMP to add some safe and smart threading, but we still have to worry about data races. Smart multi-parallel programming I can't get too deeply into that, but you can use OMP and pragmas like this to define mutexes and whatnot, and we're going to sort of think about whether that will help our fuzzer situation, or whether it's even worth worrying about. We also might think about cache optimization, which is almost always totally manual, but arranging data accesses so they always avoid making a cache hit. And again, does that work with fuzzing? Can we do an entire fuzz job and keep it in the cache? Most people think this is black magic. It's pretty approachable if you go and read the compiler docs. So there are also special caching architectures you can get if you have a Xeon Phi. They have MCD RAM and stuff like that, shared memory architectures that make it easier to have a much larger cache that more seldomly invokes the penalty. Here's the docs for that, or the description of what it is. And if you use the Intel optimizing compiler, there's even options to do it automatically, but again, you have to double check that the compiler is actually doing it. Again, we'll explore these in detail, whether it's useful for our purposes, in a sec. Or you might have a multi-house setup like the cluster we're hoping to do. But then we have to find a way to spread out our algorithm, right? We have to see a thing about like MapReduce and that kind of algorithm. Like, can we split up the action of fuzzing? Are we going to split up the generation of fuzzing test cases among multiple CPU nodes? Are we going to split up the execution? Or are we going to even do something even more wild and split up the individual parts of the process? We can sort of, with MPI, we can actually go through and say, only do this loop on certain hosts. And that can be really useful. Here's an example of like what the OpenMPI pragmas look like. This is kind of a deep topic, so we're going over it fast, but I think you guys get the idea. And then one idea that's, I'm just going to put in your mind, we're not going to explore it too deeply at all, is the idea of doing GPU acceleration. And this is like kind of the future, and NVIDIA has some really cool technology for automating these kind of optimizations, or automatically turning C code into a format that can be executed on the GPU. But for fuzzing, it's just not there. I've never seen a GPU accelerated fuzzer, so we're going to leave that. So let's talk about our tech stack for this, what this is made out of. So here's a high-level map of our architecture. So we have a job queue. We got fuzz job pre-processing. We're going to set up processing prior to things being run by the fuzzer. We're going to run our fuzzers. We're going to do some crash triage, and we're going to do sort over our output. And a big part of this that most people wouldn't be familiar with if you haven't done any like cluster computing is like that style of job queue. Sort of a script that can kick off the jobs and also measure their efficiency and say, it took this many seconds to run this algorithm. You get the idea. I went for a sort of traditional style queuing option called Torque, which is available on Ubuntu. It's pretty easy to install and gives you the same sort of API for kicking off jobs and queues and whatnot, like QStat and whatever that you would see in most college clusters. So I sort of imitated that, or imitated cluster setup Intel uses. So a lot of fuzzers will require some additional work before fuzzing can start. Traditional fuzzers may require a rule set for fuzzing outputs, some directions for where to fuzz. Our active guided fuzzers like AFL may require cross-compilation, binary instrumentation. So we upfront have to write some scripts for this thing to kick off before it can run a job. And that's going to be part of the cost of running a job. So we're just going to assume we're running AFL for guided fuzzing and BFF for traditional fuzzing. And for crash auditing tools in our experiments, we're going to use CrashWalk and AFL Crash Analyzer. Although I think I only have numbers for you later for one of those, so keep that in mind. And just to think about how we're going to string all this together, we want to think about how do we isolate triaging from fuzzing, or how do we want to keep the triage step synchronous from the fuzzing. Again, there's actually a lot of options for how you split up things across nodes and what is actually useful. And for our output, we want the largest number of good crash test cases possible, and we also want some data in which crash test cases are most interesting to us. So now we're going to consider the viability of each of these optimizations and how it potentially could work on our system, and see if that, as we go on, if any of these are viable speed ups for our scenario. So fuzzers in general have a weird bottleneck to them in that the fuzzer itself may only be doing a fraction of the work depending on the target software. Often it's possible for the target software to eclipse the amount of CPU. So really speeding up the fuzzer itself is a little bit of a waste of time, but we're still going to explore that. But it appears that a lot of the biggest gains are speeding up the execution of the test case without changing its semantics. So most of the delay has been generated as the software kicks off new iterations of the software. It's going to fork new processes. This is a big thing. If you've ever used AFL on Mac OS, this is like horrible. Fuzzer will spend a lot of its time waiting for the fuzz case and the target software to finish. It's possible to have a situation where the parent process is taking more time than the child, but it's uncommon. So first set of experiments is like, would running these SIMD operations, optimizations, AVX 512 on the fuzzer itself give us any gain? And really, in a lot of cases, the answer is no. Again, so little of the time is spent in the fuzzer itself as opposed to the host software running the test case that it's not a huge difference. I think we'll look at numbers in a second. There isn't a way to refactor this into matrix multiplication in most cases. Intel advertises maximum difference of 6 times performance in transition from AVX 256 to 512 for optimal workloads. The most I observed was about 2% speed up, switching things to AVX 512, so kind of not worth it. Then there's the reasonable consideration that maybe if we thread our fuzzing processes, we'll get some gain out of this. Problem is that most fuzzer authors have already done this and thoroughly integrated OpenMP, so we're kind of not so many opportunities to speed it up there, fortunately. It's kind of smart people doing smart things already. It's very unlikely we will find much for the fuzzer to do while it's waiting for its child jobs to finish anyway. And then there's a lot of people trying to get a good open MPI fuzzer going. I've seen experiments and papers, but nothing too finished. I think this is the preferred approach. Each fuzzer runs its own children on multiple compute nodes, and everybody meets up in the end. But one question I don't see explored quite enough is there another variation on this approach that more efficiently uses our resources? Is it possible that we could use OpenMPI pragmas to spend all of our time in the hard parts of the software to run? Is there a way to do that safely and still get the same crashes? I think that's a deeper area of research that people should explore. We're not going to bother with cache optimization for the fuzzer itself. Again, it's probably not going to work out. What about the target software? Is it possible that we might be able to safely recompile the target software with optimization so we spend less time in it when we're running our fuzz test case? In most cases is yes. Use optimizing compiler. You can sped up 20, 30 times. It's great stuff. So it's possibly worth it. But you also have to consider for yourself how much time, engineering time, you want to trade to get the speed up. And whether the targeted program is how do you say, amenable to it. In my 3D printing test cases, it really was because it had a lot of linear algebra. But in something a little more linear, it might not. So in my own tests, I'm going to give you charts in a second, I observed about 10% speed up in generations of fuzz cases for appropriate workloads as compared to control. So what about OpenMP on the target software? This gets really complicated. If you want to try and find a way to add threading that wasn't already there, and then you run into the case that it's really hard to add that without side effects and causing data races that weren't there in the original software. But there could be a possibly massive speed up if you design it correctly. Then again, if it's running on the same system as the fuzz test case generator, you're probably running out of threads anyway, so that's that. Skip over that. And then we might want to explore how we can better split up over nodes the running of the target software. I touched on that before, so we don't have to go too much deeper on that. Again, splitting up things smarter ways would be a cool idea. We tried some more creative things. It didn't work out. And what about triage software? So triage software presents an especially daunting task because crash triage software has all the problems of running the fuzz test case, but worse, because the way a lot of it works is crash triage will need to invoke a debugger for each job it's running. Then the debugger must invoke the target program and run until it crashes. And that means we're waiting around on 2 forks instead of 1, and we're waiting on a crash that might take an undefined amount of time. And currently there's no solution to that other than to parallelize everything, and it's just down to the number of nodes you have. So there's nothing to gain from SIMD, not even from OpenMP or MPI, other than the obvious thing of parallelizing it in the most obvious way you could think of. So just to sum up, what did we learn in this section? The great majority of work is in the child process. Optimizations to the fuzzer itself don't make as much difference to the overall performance as optimizations to the child processes, but optimizations have to keep the semantics of the original program. There might be opportunities to further up the ante if we set up exotic threading or MPI paradigms, but we're trading a lot of work for the results we get. So why don't we set up a fuzzer race? Learning what we've learned, how much gain can we get for our crazy fuzzing rig for the willing amount of hobbyist engineer time I'm willing to spend. So here's our very informal, possibly little unscientific experimental design. We're going to set up several of our imaginative fuzzing cluster designs and run them head on with each other, and we may learn some things from the performance. Here's my VPS setup. I did this on DigitalOcean with their high performance compute nodes. They're running Torque for control queuing and using the stacks described before, Torque, AFL Crashwalk, Torque, AFL Crash Analyzer, Torque, BFF, and Crashwalk. Again, I think I don't have BFF numbers here for you guys, so I apologize in advance. And here's my cluster, and it lives. And for our target software, I wish I'd written this talk after Trail of Bits did their talk on benchmarking fuzzers. Otherwise, I would have integrated some of the test suites they had there. But I used Objum and an old version of libmagic that I knew to have a lot of crashes. That's one of the typical go-to ones for AFL. So my parameters are this. Each fuzzer gets to run for 10 minutes. Controlled by the queuing system. I run it once in the control node, run with the trivial parallelizations, and then with more, and then with more. And here are raw results, and they kind of conform to our intuitions from before. The easiest way to get extra speed out of these things is to add extra by hand SIMD optimizations. For adding nodes obviously adds a lot of speed, but a lot of cost, so it's not the best return on investment. And OMP is kind of dicey. Someday I will get a more scientific graph on this thing. But I really hate using GNU Octave, so maybe I should just hurry up and get a mathematical license. All right, so that covers what I did. I think you guys might have questions here before I move up to some of my conclusions. So I'm going to open the floor. You guys have questions? Oh, it's quiet. I've been going so fast. Okay, sure, nobody? All right. Distributing this across multiple nodes worked very well. We already knew that. Adding some manual optimizations helps a little bit, but not enough for it to be worth it outside of a hobbyist perspective in most cases. And it's very labor intensive. If you're curious about setting up a similar situation to what I did this for about $300 a month worth of fuzzing and made kind of a good profit on it on bugs. But if they were smart about how they set it up, maybe you could do even better than I did. So it's got a doable break even. I don't think it would be any cheaper doing it with an at-home cluster and paying for your own electricity and cooling and stuff. Just back of envelope, it seems like it's not viable. We didn't add any slick continuous integration tools to this. We didn't have any automatic deployment of nodes. That might be stuff to add for the future. I'm definitely continuing this research. I really want to find a way to GPUize this. I feel like that's the future, but it's really hard to do it without side effects. I think that a lot of the future of this is doing chunks of programs instead of the whole things strategically. But it's hard. And there's all kinds of exotic solutions, neural net-based fuzzing and that kind of thing, but that's pretty much where we're at. Well, that's the end of my talk, and if you guys have any other questions, let me know. My name's John Dunlap, and here are my contact details, and you can grab the slides right here.